Next, we have the ratio test. The ratio test comes in handy when we're dealing with factorials and terms raised to the n powers. So the ratio test says that if we take the limit of the ratio of the n plus 1 term with the nth term, we will either get a limit that's less than 1, or a limit that's greater than 1, or infinite, or a limit that is equal to 1. If we get a limit that is less than 1 here, then the series is absolutely convergent, and therefore the original was convergent. If the limit's greater than 1, or if it goes to infinity, then the series diverges, and if it's equal to 1, then the ratio test is inconclusive, and we don't have an answer to our question. We would have to try something else. All right, so let's look at an example. So here, notice we have a 3 to the nth power term in our problem, which is our hint that the ratio test might be a good idea. If it were just negative 1 to the n times 1 over 3 to the n, that would be, of course, it would be a geometric series, and we would be done. So we need the n plus first term up on the top. So we have n plus 1 cubed over 3 to the n plus 1 on the top. This is absolute value, so that takes care of the negative 1 to the n. So I'm not even going to bother with the negative 1 to the n. And we're going to divide it by the n cubed over 3 to the n. I wrote it like this to save a little bit of space. And now we're going to take the reciprocal and multiply. So what we have is, well, I guess we'll write it all the way out, negative 1 to the n, and the absolute value of that. So this is the ratio test. If we end up with a limit that exists from this and a limit that's less than 1, then we're good, and it converges, and if not, we'll just have to see what we get. So here, our negative 1, like I said previously, the absolute value takes care of this alternating sign. And then we've got the limit as n approaches infinity of n plus 1 cubed over n cubed times n to the 3 to the n over 3 to the n plus 1. So now we need to know what this limit is. So I'm going to simplify as much as possible to find this limit. One thing I notice is I can write 3 to the n plus 1 as 3 to the n times 3. And I can write the n plus 1 to the third over n to the third. I could write that as all to the third power. So I've got n plus 1 over n to the third times 3 to the n over 3 to the n times 3 to the first. Okay, so this cancels, and now the only place that we have n's is right here. And if we want, we could rewrite this in the following form. Notice we've got a common denominator of n there, so we can split up the fraction and write 1 plus 1 over n cubed times 1 over 3. So now, as we allow n to approach infinity, we have 1 plus 0 cubed times 1/3 is 1/3. All right, well, 1/3 is smaller than 1, so our original series is absolutely convergent. Our next problem, determine the convergence of the series. Okay, well, we said previously when we have raised to the n power, or if we have factorials, then we should suspect the ratio test. Now, what's a factorial? Just as a reminder, for example, 5 factorial is 5 times 4 times 3 times 2 times 1, right? So, just a reminder there. So that's n times n minus 1 times n minus 2 all the way down to 1. Doing the ratio tests, we have, well, before I do the ratio test, I want to point out that n is a positive number. The denominator will be positive, and the numerator will also be positive since we're raising a positive number to the positive number. So it doesn't matter. We don't need to use the absolute value. We could just skip that part. So we have n plus 1 to the n plus 1 divided by n plus 1 factorial divided by n to the n over n factorial. We want to take the limit as n approaches infinity. So let's take the reciprocal and take a look at this fraction, see what we can come up with. We have on the first part, we have n plus 1 to the n plus 1 over n to the n times n plus 1 factorial over n factorial. My goal is to simplify this as much as possible in order to take my limit. So I'm thinking we try something like we did before, see if we can split things up in order to cancel things out. Because of the way factorials work, n plus 1 factorial is n plus 1 times n times and so on. So I'm going to write that as n plus 1 times n factorial over n factorial. So that's my second part of the fraction. What about this first part of our fraction here? What can we do with it? You know, it would be better if we had a to the nth power instead of a to the n plus 1 power. So I'm going to just go n plus 1 to the nth power times n plus 1 over n to the n. So I use that same technique as before. Here, n factorial and n factorial, those are the same amounts. Next, I can combine my fractions together a little bit. So what do we have that we can combine? Except that I just noticed that I got my fraction over here flipped over. So this fraction should be flipped over. Sorry about that. So if I flip that fraction over, that means I've got an n plus 1 in the denominator. Okay, that makes things a little bit nicer. So that n plus 1 in the denominator will cancel with that n plus 1 in the numerator. But I still have to deal with this n plus 1 over n to the nth power limit. Now this is a special limit that we may have seen previously, like in Cal 1, but it looks like we might have a 1 for the inside stuff raised to the infinity power. If you remember, that's one of those indeterminate limits where you can use L'Hopital's rule. And if you do use L'Hopital's rule, you need to change its form from 1 to the infinity to infinity divided by infinity or 0 divided by 0. So I'm not going to go through all of that, but this thing works out to be just E. See Calc 1, L'Hopital's rule. So that's comes from the definition of E, or you can go back to L'Hopital's rule and see how we get that. But what is E? E is greater than 1, so what that means is this this fails the ratio test, and now we have a series that is divergent.